Welcome everyone. Thank you for taking the time to join us for our webinar today. And I'm very happy to see many of you here and many familiar names and faces, so to speak. Okay. Now this is our second webinar, and then there will be more to come. So please keep your eyes open, and we'll announce the next few ones. And we've lined up some speakers, so we'll let you know who they are very soon, and an exciting series of talks. Okay, so let me introduce our first speaker today, and we have Sarah Masters. Sarah is currently at the University of Canterbury in Christchurch, New Zealand. And her research is geared towards providing structural information about transient, short-lived species. And Sarah received her PhD from the University of Edinburgh, and has been at the University of Canterbury since 2000 and remind me. 11. Great, that's what I thought. Okay, Sarah, without any further introduction, please take it away, and happy to see you here.
Kia ora koutou, nā mai haere mai. Hello everybody, and welcome. I can't actually see any of you because my screens are all set up for the talk, so all I can see is a number of people, so hopefully that goes up and not down. So my understanding of these webinars is that there is one which is more experimentally based, and then one which is more about theory. So I do both, and so the title of the talk that I sent round is not experiment plus theory equals awesome, but that's what I think. Okay, and many of you have seen this picture before. This is of course Mount Cook, and it does actually look like that at the moment as well. And we've got some lovely snow on the Alps here. Unfortunately, none of you can come skiing, but we can. So I thought I'd open with this particular question here, which is, what is the structure of this molecule? So this is tris-chloromethyl amine, and there are various options on the screen here. And I'll come back to this, and we'll talk about this in much more detail a little bit later on. But another question would be, how would you go about finding out what the structure of this molecule is? And that's what I do. So I'm an experimental gas phase chemist who does some computational chemistry as well. And so I'm very, very interested in molecular structure and how we determine molecular structure. And there are lots of different techniques out there that you can use. So I've just outlined a few on the screen here. So in this, it really depends on which phase you're working in. So in the solid phase, and obviously X-ray diffraction is the go-to technique. It's pretty ubiquitous in chemistry departments around the world. Liquid phase is a little bit more challenging. There are various techniques that you can use though. And then for the gas phase, there are a few groups around the world who do gas electron diffraction, and I'm one of them. Those of you who know me will know that I'm unique. And in terms of gas phase chemistry, we're quite rare as well. There's not very many of us around. And then there are also obviously lots of spectroscopic techniques that you can use as well, and these will be familiar to many of you. So today I'll talk a little bit about some X-ray diffraction. I'll talk about gas electron diffraction, and also Raman spectroscopy as well. And I'm not sure who the Raman spectroscopists in Australia are, but this is a collaboration with Mark Waterland here in New Zealand. So I'll talk a little bit more about that as we go. Now, I'm conscious that many of you may not have heard of gas electron diffraction before. It's a gas phase technique, as I say. There's very few groups around the world who actually use it. And so I thought I would just outline a little bit about what it's about and how we can get the data from it. So on the screen, you can see my electron diffractometer. And this is it in its nice new shiny lab here at the University of Canterbury. And hopefully you can see my pointer, it's the red dot. And so this is the electron gun. Okay, so shiny bit there is the electron gun, and that's because it's an electron diffraction technique, and so what we are shooting at the molecules are electrons. And this is obviously a charged beam, and so we can accelerate that electron beam through an anode-cathode arrangement, which is around about here in the electron gun. And then we focus the beam using a series of lenses and apertures at around about this point here. We then pass that beam into a diffraction chamber, which is actually right down the other end of the apparatus. And then we have a mechanism to get our sample into the apparatus, and obviously it's a gas phase technique, and so quite often we have to heat our samples up to get them into the gas phase. And so more often than not, we're using a high temperature inlet to heat our sample up, which is out here somewhere, and then fire it into the machine. And the idea is that our molecular beam and our electron beam interact at right angles, and then our electrons in the electron beam are diffracted by atoms within the molecule and detected on a detector. And I don't know if Scott Cable is online or not. It's a bit of an ongoing joke, and yes, we are still using the films, Scott. Still haven't got a CCD camera on there yet, if you're watching, but they work, and that's good. We also obviously have to have our system under a vacuum, because otherwise we will have other molecules in there that we don't want to diffract off. And so just behind here, you can see this big green gate valve, which leads into turbo pump system. And then we also have a cold trap on our system as well. And what this does, this is has liquid nitrogen in here, and this sits at the top of that diffraction chamber. And so when our sample comes into the apparatus, we can then, once the diffraction has taken place, condense our sample onto the cold trap, and that prevents secondary and tertiary diffraction along the electron beam for our scattered electrons. And so this is our equipment. This is how we do it. And I should have said for the electron gun, we've got a 40,000 electron volt source going in that end. So when it's on, then we tend to stay down the other end, down the detector end. Okay. So what do we get out of our experiment? Well, before I even moved to the Southern Hemisphere, we got what we call the wiggles. And so it's even more relevant now that I'm talking to an Australian audience. And so we get the molecular intensity scattering curve, which is literally a set of wiggles on the screen. And what this is, it's a plot of intensity against distance from the center of our diffraction pattern. And that's all well and good, but we can't really identify what our molecule is just from looking at this. Well, I can't anyway. And so instead, what we do is we apply Fourier transform so that we end up with a radial distribution curve. So we have a plot of the probability of finding the distance plotted against the distance, and we get these series of peaks here, which is approximate Gaussian shaped peaks. And each of these peaks represents an internuclear distance within our molecule, both bonded, so in this lower region here, and non-bonded. And the sticks represent the actual internuclear distances. And this is very useful because if we get several internuclear distances which are similar, then we can deconvolute them out of our data. So my system seems to have frozen, so just give me a moment. There we go. So why bother? Why do we bother trying to get gas phase data? Well, as I say, there's not very many of us, but we are important, or we like to think that we're important, because what we're getting is structural data which is free from the intermolecular interactions which can really affect solid state structure. So we're not getting that hydrogen bonding, for example, and all the other dipole effects as well that can affect solid state structure. That isn't to say that the solid state structure is incorrect, it just means it might not be the same as the gas phase structure, and that's important to remember. And we'll see that as we go through this talk. We also get internuclear distances, or very close to internuclear distances, so we tend to get more accurate bond lengths than you would perhaps from X-ray diffraction, given that we are diffracting off the electric field gradient between the nucleus and the electrons in an atom rather than the electron field. So, as we have gone through the years, there's been a lot of apparatus development, and as a consequence, we can now look at much larger molecules in the gas phase, which is great, only it then means that quite often we can't get a complete molecular structure from gas phase data alone. And so we have to look to other data to try and understand and interpret what's going on. And so to do that, more often than not, we will use theory, and hence the title that I put at the beginning, saying experiment plus theory equals awesome. So in a combination of experimental and theoretical data, then we can get a complete molecular structure. So the background here, this has been color enhanced. Obviously, this was a cover of a journal from a few years ago, but you can see the diffraction patterns that we get. From this, we can extract our molecular scattering curve, and then from that we can combine it with theoretical data to get a complete molecular structure. And at the time that this was done, this is octaphenyl silsesquioxane. This was the largest structure that had ever been looked at using electron diffraction. And so the process of combining theoretical and experimental data together in this way, there are different ways that we can do it, and we like our acronyms in the group. So we have the Saracen method, the dynamite method, or the Semtex method. So this is, Saracen is where we can combine structure analysis restrained by ab initio calculations for electron diffraction. So using our ab initio calculations as restraints or extra observations within the data. And then dynamite and Semtex are more dynamic interaction of theory and experiment. So once again, it's just taking a wee moment to change screen. So hopefully that will change in a moment. My screen's just frozen up a wee bit, but we can use other types of data as well. So it isn't just computational data that we can use. There we go. So we can use information from rotational spectroscopy, for example, from NMR, and all of the corrections that we can obtain from computational methods as well. And we can combine these together to get really the best of both worlds and to get a complete molecular structure. Okay, so I come back to the original question, which was, what is the molecular structure of this particular molecule? So this is, as I said, trischloromethylamine. And so we've got this various different options on the screen here. And the structural investigations that we undertook for this molecule are very wide-ranging. And I should say that this investigation took around about 20 years to complete, and I'll explain why later, but it's really all to do with actually the development of the computational side of things rather than the experimental side. So we could do the experiments, but interpreting the data was really, really difficult. So if in the solid state, we did X-ray crystallography, well, I say we, so this sample actually originally came from Tom Klapötke, and anybody who's worked with him always has a bit of a rush of adrenaline whenever you get a compound from him, because they tend to be pretty explosive. This one wasn't, fortunately, but he's very well known for his high energy molecules that he works with. We obviously did some computational methods and investigation there, our electron diffraction experiment, and also our solid and melt state Raman spectroscopy. So let's start with the solid state. So space group Pnma, I'm a gas phase chemist, but basically this is a nearly planar amine in the center of our molecule, but it's got what we call a bar stool arrangement. I don't know, I can't see myself on the screen. I don't know if you can see my hand, but it's like a tripodal arrangement, and all three of the chlorine atoms in the chloromethyl groups are pointing downwards with respect to that almost planar central nitrogen there. Okay, so the angles, the CNC angles in this, they're not quite 120 degrees, but they're getting pretty close to it. Okay. And there's quite a strong dipole within this system as well, and I'll come back to that point again a little bit later on. Okay, so if Lars is watching, I don't know if he is, I know he's based in Melbourne. If you're watching, Lars, just look away now. And I would point out and remind you again that this molecule has been kicking around for 20 years. And at one point, B3LYP was acceptable. But anyway, we did some initial gas phase calculations. And we were having some real challenges trying to identify a minimum on the potential energy surface for this molecule. So we knew what the solid state structure was, because obviously we've got the crystallographic investigation, but trying to find the gas phase structure or conformers was a bit more challenging. So what we did find, however, was that this structure on the left, where we've got one of our chloromethyl groups is flipped round, has done a 180 and is pointing up with respect to that central amine, whereas the other two are pointing down. And then we found the structure shown on the right here, where one of these groups is moved off by about, I think it's about 20 odd degrees. And there's obviously a mirror image of this as well, but we can't differentiate between that, those mirror images within our gas phase data that we obtain. So we tried to fit a model of this to our gas phase data. So the data was collected at around about 400 Kelvin, but the model really did not fit well at all. And what we were finding in particular was that we were getting some really ridiculous vibrational corrections which were associated with these hydrogen atoms, which are sitting on that unique chloromethyl group. And so this leads into a discussion around vibration and the effects of vibration on gas phase data, particularly at slightly higher temperatures. So when we do our theory calculations, then we're calculating an equilibrium structure. But what we obtain from electron diffraction out of our data are structures which are averaged over many vibrational states. So it's not just that equilibrium structure, there's a whole load of structures in there. And it's fair to say that our vibrations, so we have vibrations along a bond axis, which is fine, and then we've got vibrations which are perpendicular to the bond axis. And these vibrations which are perpendicular to the bond axis can actually have a real significant effect on our final structure. And so we have to correct for all of this vibrational effects in our models that we then fit to our experimental data. And so this is what we call a shrinkage correction approach that we apply. And so every pair of atoms in our molecule will have a shrinkage correction associated with it. And I've just given in our diagram here an example. This could be something like carbon dioxide, for example. And we all know that carbon dioxide is a linear molecule. However, if we were to take electron diffraction data of it and just analyze the raw data and not do any corrections at all to it for vibrational effects, then we would actually observe carbon dioxide to be the vibrationally averaged structure, which would not be linear. And so that just shows the importance of vibrational corrections. And so we have to correct back down and correct for these perpendicular vibrations within our system. We have a way of doing this, so we can use what's called the shrink code and shrinkage obviously being what happens when we apply those vibrations. So we extrapolate using our force constants from our equilibrium geometry, and generally these are harmonic force constants that we're applying. And that's all well and good for most systems, that works fine. However, when we have large amplitude motions within our molecule, then these traditional corrections, vibrational corrections, don't work so well. And so what do we do if we have a large amplitude motion? Well, we just do more calculations. And so hopefully, Lars, if you're online, then this functional that we're using here will be a little bit more acceptable to you. So this is calculations that were done a lot more recently. And so what we're doing here is we're investigating rotation around that nitrogen-carbon bond of the unique chloromethyl group. And so structure B, which is shown here, this is the solid state structure. So when we rotate around that CN bond, we do find our solid state structure as a minimum on our potential energy surface. And then we also find what we believe is the gas phase structure. But if you look at this potential well here, you can see this is really, really flat over quite a wide angle range. Okay, and so we really do have a very large amplitude motion associated with this unique group, and therefore we have to try and come up with some corrections for this. And so the solution that we have is something more than shrink, obviously, and this is using vibrational corrections from molecular dynamics methods, and that's why we had to wait for so long to try and solve the structure of this system. Okay. So what molecular dynamics allowed us to do is to firstly get some corrections at the correct temperature, obviously, and so we got single step distance corrections, amplitudes of vibration, and most importantly these anharmonicity constants, and these are the things that are really, really critical within the system, extracted from a 0.25 nanosecond time step within our semi-empirical MD calculations. Okay. And this MD sim program is an in-house program that was built in Ivanovo in Russia to extract all this information out for us. So now, when we fit this to our data, we get a really nice fit of our model to our electron diffraction data that we collected from our experiment. We can see all the different internuclear distances here. Importantly as well, we can see a nice flat difference curve between the model and the experimental data. So this is a really pleasing outcome. And for those who know about R factors, anything less than 10% is good. 9.7, we're on the edge, but we'll take it given the large amplitude motion that we have in this system. And I said that I would mention Raman spectroscopy, and so this is just the spectroscopy of the solid state, and then as we heat it up. So A to B to C is going from essentially room temperature up to about 100 degrees C or 393 Kelvin. And you can see that apart from some broadening of the bands, there's very little change in the system here. D is the solid state spectrum as predicted from our calculations, and E is the gas phase spectrum as predicted from our calculations. Now, given that A is definitely a solid and C is definitely a melt, and there's very little difference between these two spectra, what we can say is that the melt structure is very, very similar to the solid state structure, and there is a very large dipole which is stabilizing that solid state structure, and that appears to hold in the melt. Before anybody asks, the one thing I don't know is how long we actually left it in the melt state and whether it would eventually flip round into that gas phase structure. So that's something I need to go back and actually ask Mark, because I've only just thought of that as I'm talking. Okay, and so just to summarize, the gas phase conformer is a pseudo-rotameric structure of our solid state conformer, and we only see this conformer in the gas phase. We don't see it in the melt state under the conditions of the experiment or the solid state. But all the vibrational corrections that we had in our toolbox were not sufficient to analyze that gas phase structure, and we really needed that molecular dynamics approach, which is why it took so long to do in the end. Okay. So finally, just to thank a few people, this work was done in collaboration with Derek Wan at the University of York, who actually started in the Edinburgh group when this data was collected many moons ago, and also Mark Waterland at Massey, who did the Raman spectroscopy for us, and Sandra was a very talented PhD student who worked with me in my group here at Canterbury. Various sources of funding from UC and also the Royal Society of Chemistry in the UK, and the now regretfully defunct National Service for Computational Chemistry Software, which was in the UK and was a fantastic resource, and I'm very, very sad that that is no longer working. Okay, so thank you very much for your time, and Tak, I'm sure there are some questions and I'm happy to try and answer them for you.
Thank you very much, Sarah. On behalf of everyone here, I thank you for your talk. Appreciate it. Yes, we do have some questions, and the first question is actually asked by Evan. So We have a bit of time, so I think I'll unmute the people who ask questions so you can have conversation. So Evan, I'll unmute you if you don't mind. Okay, so Evan Robertson asked the question: is the sensitivity sufficient? This is the experiment to perform jet experiments and hence cool the row vibe populations.
Yeah, absolutely. So that's hi Evan, how you doing? So that's certainly something that's yes, basically. So, just trying to let me get my words in the right order. So what we can do, and certainly something that I've always wanted to do, is to essentially vibrationally select which conformers are actually going into the machine. So doing that using so-called state-specific electron diffraction or a supersonic expansion. So then it's a supercooled beam, and you can choose what it is that you're putting into the machine. So I think that's what you're asking.
Yeah. So is that done elsewhere or?
No.
Oh, no. You could be the first.
It's always been yeah. How many grant applications for that one? I don't actually have the capability to do it here at UC, but Derek, my collaborator in the UK, does have the capability to do it with his equipment. So yeah, absolutely, it's on the agenda. Lots of things are on the agenda. Cool. Lovely to see you though.
Thanks, Evan. The next question is from Chris, which is a bit of an interesting one. How tall does the operator need to be to open a gate valve?
Yeah, okay. So there was a minimum requirement of 6 foot in my doctoral students, but I do have a step that I can stand on. Most of you know me, I'm not very tall, but fortunately our technician is really quite large, and he can, or well, tall anyway, so he can reach to it. Yeah, absolutely. Yeah. Actually, the gate valve's not the problem. It's getting bits on and off the equipment is the challenge, because they're really actually very, very heavy, and you need somebody with a bit of muscle underneath it. So being in New Zealand with lots of rugby players, that helps.
Any follow-up questions, Chris? Take that as a no. All right. Yeah, that's a very impressive spectrometer there. Now, the next question comes from Juan. Juan is a student of Laura. Did you compare the vibrations to reference data? Maybe I'll unmute Juan to actually be more specific. So, so Juan, which are you referring to a particular slide?
Oh, hi. No. So when she was saying that she did some calculations for the vibrational frequencies, and some of them were a bit off. So I wanted to know, like, if you were comparing those vibrational frequencies with some reference data.
Right, okay, not specifically, but what we get from those calculations are a set of vibrational corrections, and we know from experience what ballpark figures we would be expecting for those vibrational corrections, and when they're 10 to 100 times the size that we would be expecting, then that indicates that there's something a little bit amiss with the corrections that we're getting from our traditional methods, and that's why we had to move to using the molecular dynamics. Yeah.
Yeah, okay, thank you.
Cool.
Great, cheers. Now the next question comes from Terry. And how do the B3 lib MP2 wells compare to the SEMM MDFF?
Yeah, sure. Hi Terry, good to see you again. Yeah, cold. So how do they compare? Actually quite well. Sorry Lars, but they do. But it's more about the vibrational correction side of it, and using because we had the opportunity to use more sophisticated DFT methods, then we took that opportunity.
So in your best methods, it looks like you should have a triple whirl there for that rotation. Is that right?
Triple well, sorry. On that big well at the bottom, the big wide one, no, double.
There's that 20-degree canted on either side, and then the one in the middle?
The one in the middle is actually just a transition state.
Okay.
Just about, yeah. So it's like a double well, but with an incredibly small, almost barrierless, but very, very small barrier. Yep.
And your semi-empirical method gives you something similar to that?
Yeah.
it looks like, wait,
So Lars says B3LYP geometries are actually okay. Good, thank you, Lars.
there's a, just above that, is the umbrella motion possible for this? I think that's a...
Pass. Don't know. I can't answer that at the moment. We don't observe it. I don't know what the barrier is to it, actually. I don't think we actually calculated the barrier to that. It would be odd just because of the substitutions that we've got on those methyl groups. If it's just methyl groups, then you could sort of, it would be easier to follow, if you see what I mean. Whereas when we've got the chloro there as well, umbrella as an inversion, yeah. Anything's possible. It probably does, but we wouldn't see that in our electron diffraction experiment for sure, and we didn't try and calculate it. How's that?
Okay, next question comes from our next speaker, upcoming speaker, Peter Kraus. I've been told that hydrogen atom vibration in ab initio MD don't recover anharmonicity. Any comments? Peter?
No. So what I can say is that the corrections that we got for the vibrational corrections that we got from that method and from the extracting from the MD data were great, whereas the ones that we were using from our traditional methods just failed completely. So I can't comment on your point, unfortunately, because, well, we didn't see that. So
I was
yeah.
arguing with a reviewer about this, so I'm happy that there is somebody on
yeah, okay. So
our side as well.
yeah, well, yeah, I'm happy to talk offline about that, because certainly from what we observed, we were able to get all of the vibrational corrections that we need, and it was those two hydrogen atoms that was sitting on that chloromethyl group, that unique one, that were causing all of the problems for our modeling. Yeah.
Cool,
Great.
thanks.
Our last question from the first talk is from Jyoti Campbell. What additional info does a melt state structure give you as opposed to just using the gas and solid state structures?
Yeah, okay, so it's another fluid phase structure, I guess, and what we were looking to see is what happens between the solid state and the gas phase. So it's often unclear because obviously the sample is a solid at room temperature, and then we had to heat it up to get the gas phase experiment, and so is it a case that as you heat it up, as the thing melts, that it's then the structure is rearranging at that point, or is it just as it goes from the melt into the gas phase that it's rearranging? And so it's as it goes from the, well, as far as we can make out anyway, as it goes from the melt to the gas phase, that this rearrangement is happening. And that's because you've lost all those short range interactions between the molecules that you still get in the melt. So all of that dipole effect, if it essentially disappears in the gas phase, and then you could see from that potential energy surface that I posted that the gas phase conformation, regardless of that big flat well, is lower in energy than the solid state structure, and so the solid state is stabilized by all of that dipole, and we believe that's what's happening in the melt, and then the gas is free of all of that, and so you get that structural rearrangement happening.
Excellent.
Cool.
All right. There may be, I think there's one last question. I think it's from David Wilson.
Mm-hmm.
How large are the enharmonic effects? I've worked with NF3.
Mm-hmm.
Maybe I'll just, it's a very long question, so I'm going to unmute Dave. And then
Yeah, so I can see the question on the screen. Yeah, big enough to screw everything up when you try and use a traditional correction, put it that way. I don't quite know what you mean by how large.
Well, I guess how significant, if you're looking at, comparing harmonic and anharmonic, that I'm assuming that would be quite substantial for these systems.
Yeah, I don't have exact numbers to hand, unfortunately, but yes, it was the anharmonicity of that motion that was causing all of the problems. Yeah.
Okay.
Yeah.
Right.
I'm just trying to. Sorry. No, go on.
Sarah, we might have to stop it here.
Yeah, it's just to say some very, very low frequency wave numbers coming out for that motion, which might go some way towards explaining it. Okay.
Really like your background, I think.
Yeah, so that's a guy in Australia who draws these. He's on Twitter, called Chemscrapes. So yeah, I like it.
Very cute.
Cool.
Sarah, thank you very much.
No problem at all. Thank you. It's lovely to see lots of familiar faces. Thank you for coming.
Very good to see you. Right, I'll ask you to unshare your screen here, and then so we can get Peter on. So our next speaker is Peter Kraus from Sarah. Have you unshared? Yeah, you have. Okay, right. Okay. Our next speaker is Peter. So Peter, maybe you can share yours now. Let me know when you have. Okay, great. Okay, Peter is currently at Curtin University. He's a Forrest Fellow. Now, this is a fellowship that is that supports an independent early career researcher. And Peter received his PhD at the Imperial College London. And the goal of Peter's research is to actually, this is an interesting one, to produce a cookbook of computational methods for predicting electrical conductivity of materials under operating real-world conditions, incorporating the effects of the environment. So I will let Peter elaborate. And Peter, it's very good to see you here.
Thanks a lot for the invitation and the introduction. I'm very happy to be here. I am very new in Perth. I only moved here in February, so unfortunately I didn't get to meet many of you in person, but maybe that's going to change some point soon. I will not talk about my main project here in Perth. I'll talk about some stuff I did over the last few years, about my contributions to Psi4. I tried to make this talk interesting to both people who might not do much quantum chemistry, and I tried to include some hands-on examples of what I've been doing recently. So, what is Psi4? Psi4 is a quantum chemical package that allows one to calculate things like density functional theory, coupled cluster theory, symmetry adapted perturbation theory, and so on. The reason why I like Psi4 quite a lot is that it's open source and that it has a Python interface, which means that all the heavy lifting is done behind the scenes in C++ coded routines, but all the objects are available through Python, so it's incredibly easy to use. I should mention that there are other very good codes that one could use, for example, for coupled cluster theory or multi-reference coupled cluster theory. There's C4 and MRCC, which are probably better at the things they do than Psi4 is. However, we have an interface to these two codes written in Psi4, so you can integrate them into your workflow seamlessly. Then if you are after density functional theory, there are also packages which might be quicker or have more functionals. For example, the DFTD4 functionals from Stefan Grimme's group are not yet implemented in Psi4, but I believe they are now implemented in Orca. Also, if you are after another code which can be driven using Python, then PySCF is another alternative with the added benefit that it can also do plane wave calculations, not only Gaussian atomic orbital calculations. And there are cases where you might want to use Gaussian as well. So why do I use Psi4? Well, this started, as most of the good stories do, in a beer garden in Hanover, in Germany. And I was having a chat with some of my colleagues, and the conversation went something like this. Our paper got rejected, so I asked why. And they said, well, we use B3lib. So my remark was, well, it is 2018. We shouldn't really be using B3lib anymore. I appreciate the irony of this statement with regards to the previous talk. Anyway, what we were actually looking at was something very similar to what Sarah is doing. So this was a group of microwave spectroscopists, and they were investigating van der Waals complexes at the time. And what turned out to be the case that there was actually no clear guide about which density functionals are good for specifically predicting the structures of van der Waals complexes. And the problem in microwave spectroscopy is that although you can get the information about the structure directly from the experiment because you get the rotational constants or the moments of inertia, to actually know where to look for the signals, you should have a decent guess for your initial structure. So we did a database of 16 van der Waals complexes, did this correction from the ground state average structure to the equilibrium structure, which you get from theory. And then I have benchmarked quite a few functionals, a selection of which is shown over here. On the x-axis is the mean difference over the non-covalent bonds in the structure. So I have highlighted, oops, wrong key. I have highlighted B3lib down here on the bottom. Well, that doesn't work here. So B3lib is third from the bottom with an error of 1400 milliangstrom. So if you use it for non-covalently bound complex, you will obviously fail. However, once you apply dispersion corrections, such as in the B3lib D3BJ, if you look on the left-hand side, I think it's the 6th or 7th on the list, you actually get a very respectable structure. So not all hope is lost for B3lib. Why I think you should use Psi4 though is that it has a very open development. So we are on GitHub, we are on Slack. One of the things why I really like working with this team is that they are very welcoming to any sort of contributions. You can see it, you can see it on the amount of contributors that are authors on the latest Psi4 paper. I think there are 20 institutions involved, and quite a few people such as me or Holger Kruse or Susi Lehtola are not associated with any of the American institutions that are the chief contributors to Psi4, but we have been accepted in the community, and it's really open source as it should be done. If you are, on the other hand, interested in an educational resource, I should refer you to the very recent paper by Ashley McDonald. So she used Psi4 as the quantum chemical package to teach undergraduate students quantum chemistry. And I think this is really an important area of science, and there are toolkits and there are labs developed. You can download them from the Psi4 website or look at her paper. Another important reason, a bit more technical, why I like working with Psi4 is that it's incorporated into the MOL SSI workflow, especially the QC archive project. And this is the idea that we should really try to standardize the way we do inputs for quantum chemical calculations. So I'll show you an example of 3 different inputs that you can do the same calculation of a neon dimer with CCSDT with triple zeta basis set. On the left-hand side is essentially a standard input file like you write for almost any other code, and you execute it using the Psi4 command. In the middle, it's something we call internally as Psi API. So you can import Psi4 as a package into your Python script or into your Python code. And then you can essentially just translate the commands you use within the normal input file into the Psi4 namespace, and you can execute it as part of your Python scripts. So this is, for example, how I did the benchmarking on the previous slides with those 80 functionals. I just had a script that ran through all of those 16 complexes and so on. And this makes the use very easy. The most recent development in this area is that we have incorporated QC schema, which is essentially a schematic description of the quantum chemical calculation itself. It's in a JSON format, so it's both human readable and machine understandable. And the really nice thing about it is that it spits out another JSON file. So apart from the normal output, it returns a JSON file, which is all the important things you might want to look at 5 years down the line. Which version of the code, when was it executed, what platform was it executed on, and so on. So it gives you a really nicely packaged input-output combination, which is really good for reproducibility. And finally, for the hardcore quantum chemists around here, one of the nicest resources at Psi4 is the Psi4 NumPy interface. So this was written again by a very large community. I wasn't part of it. But the power behind this is that all the wave function elements and all the orbital and basis set descriptions are exposed to you as a programmer using NumPy arrays. So I'll show you a picture from the paper. This is essentially what it took to implement TDDFT into Psi4. It's literally 15 lines of code, and because the matrix elements of the wave function are the occupied and virtual orbitals are NumPy arrays, you can do matrix algebra with them very easy without having to code it in C++ yourself. So what is new in version 1.4? One of the things I mentioned, or I talked about partially, is a distributed driver. So this is a rather convoluted figure, but imagine you want to do a rather complicated calculation, which involves doing something called CBS, complete basis set, or extrapolation method, where you combine multiple calculations and get the final energy. If you want to do it in a gradient, so geometry optimization, or in a Hessian, so frequency calculation, you might, if it doesn't have an analytical form, you might want to do it by finite differences. And top of that, you might want to correct for example, counterpoise effects. So previously, all those things had to be executed linearly, but now the driver is clever enough to actually split these large chunks into smaller elements that at the bottom correspond to something called a atomic input each. So it's the actual final analytic calculation. And the nice thing about this is that these can be parallelizable on clusters very easily. So if you want to do, like I did recently, a calculation which for a Hessian you would need 350 finite difference points, then instead of doing them one by one, you know, on 14 or whatever cores, but you can actually do each of them separately, and the code is clever enough to be able to glue it back together. Secondly, we have faster DFT calculations. Also, other methods are much faster than they were in version 1.1, but I'm using DFT as an example because that's the one I'm most comfortable with. So on the x-axis, I'm showing you the version number, and the different colors are, the green one is 1 core and the brown one is 16 cores. So as you see in 1.1, 3 years ago, there was some speed up when you used more cores, but it really wasn't that great. Now in version 1.4, we have speed up on a single core calculation, so it takes about half the time as it used to, as well as the multiple core scaling is much better. So it's worth actually doing DFT in Psi4, especially for range separated functionals, which now the density fitting routines for the SEF self-consistent field term are available for range separated functionals as well. And finally, there are new features. Some of them I mentioned. For example, TDDFT is now merged into the master, and there is many symmetry adapted perturbation theory improvements if you want to do non-covalent interaction studies. So I would like to talk about two very recent applications where I used Psi4 to a good effect. And one of them is a work I did in Hanover with the rotational spectroscopy group of Jens Grabo. And we looked at xenon OCS experimentally and other analogs of the structure computationally. So here I'm presenting a structure, overlaid structure of all these complexes. So helium, neon, argon, krypton, xenon, and mercury. The helium structure and the neon structure is not particularly reliable. The xenon structure we were able to determine, and the mercury structure was already, so the rotational constants were already published. We have calculated the semi-experimental structure. So it's an experimental structure that is back-corrected back to the equilibrium theoretical structure using anharmonic corrections. What was really interesting to look at with Psi4 was how to try to explain this shift between mercury and all the air gas atoms, because you can see that the position of the mercury is a little bit down. The angle is about 4 degrees higher than for xenon, and the bond distance is also shorter. And this is due to the additional induction contribution that mercury OCS has. So as you go down the rare gas group, you increase the electrostatic contribution because the polarizability of the rare gas atom increases. But with mercury, there's an additional induction term. And this induction term is actually the induction exchange term. So it's some sort of charge penetration term or orbital overlap, if you believe in those sort of things. The other part of the story was chasing experimental accuracy with wave function theory. So for xenon OCS, the nice thing is that xenon has, I think, 6 easily accessible isotopes. What this means that you can look for all of them, and because OCS has also a few isotopologues, we were able to measure 9 isotopologues. So each of them gives you 3 rotational constants, and it's only 4 atoms. So you can fit not only the structure itself, but you can also fit the centrifugal distortion constants using something called the mass-weighted structure, mass-dependent structure. So that's the RM2 structure in the middle, indicated by the downwards triangle. On the left-hand panel, I'm showing you if we do a composite wave function theory calculation, which is based on MP2 extrapolated to the limit using quadruple and quintuple zeta, so quite an expensive calculation. And then on top of that, CCSDT extrapolated using, well, on its own, first triple zeta, then quadruple zeta, and then extrapolated triple and quadruple zeta. You can see that the green line shows you it seems to be converging towards the right. So it doesn't actually explain the difference in the carbon to xenon distance. When we add all electron correlation to the mix, it actually decreases the quality of the results. So if it's an additive correction, it decreases the quality of the results. What I found very surprising was that actually augmentation of these basis sets, even though they are relatively large basis sets, a quintuple zeta correlation consistent basis set is huge, and the quadruple zeta is also quite large. But even then, augmenting them by diffuse functions brings the structure from the green point in the right-hand side to the black point. So it's within, I think it's within 5 milliangstroms, which is really, really accurate for a non-covalent complex. Also, what is interesting is that although relativistic effects are considered in the electron core potential of these basis sets, especially for xenon, when one incorporates Douglas-Kroll-Hess Hamiltonian into the mix, it actually also improves agreement with the results. I believe this is more of a right answer for the wrong reasons, because some of the scalar relativistic effects will be double counted, but it shows that there is a relativistic contribution that is non-negligible. In the final piece of work I have recently submitted and is available on ChemArchive for everybody to read is developing basis set extrapolations for density functional theory. So an extrapolation, I'm showing you the equation on the bottom left. So you can imagine an extrapolation technique essentially is trying to solve this equation where you have an unknown energy at an infinite basis set size, but you have multiple energies at a known basis set size with a cardinality x. So that's your 2, 3, or 4, or 5, depending on the size of the basis set. And then alpha is the extrapolation parameter, and f is some sort of a function that fits this difference. And because the energy is variational with basis set size, it's a negative correction. So first I looked at Hartree-Fock using 3 different approaches listed on the top left. And here you should look at the green triangle in the middle of the graphs and the position with respect to the basis to the data set. So this is a data set of 70 diatomic molecules for which the complete basis set value is known. So they have been evaluated numerically. And you can see that whatever function you use, actually the mean sits in the middle. I have color-coded those diatomics based on whether they are anions, which is in blue, neutral compounds, which are in green, and cations, which are in red. And that highlights that actually anions are the ones that converge towards the basis set much slower. And this is known because the extra electron is a bit harder to describe. And it's also interesting to look at it in a matrix format. So here in rows are the charges, and in columns are the multiplicities of the molecules. I would like to point your attention to the rightmost column, which shows you that the average or the median ideal extrapolation constant is 1.08. This is for the exponential extrapolation. For anions, 1.45 for neutral molecules, and 1.59 for cations, although there was only 6 cations in the data set. So this might be a way how to improve the extrapolation of the Hartree-Fock itself. The problem with extrapolating DFT is that it was thought that it's not really worth it from time perspective. So correlation theory scales much slower and converges to the basis set limit much slower than Hartree-Fock. And the same was thought to be true for DFT, that DFT actually is similar to Hartree-Fock, so it should converge to the basis set much quickly. And however, there are, in my opinion, a lot of interesting molecules in the sort of 50 to 100 atom size, for which the highest affordable level of theory is a density functional theory of any kind with triple zeta basis set. So you cannot afford a quadruple zeta basis set, which would definitely give you a more, well, maybe not more accurate with respect to experiment, but more accurate in terms of quality of the calculation answer. So is there room for extrapolating from double and triple zeta basis sets in DFT? First of all, I had a look at the dependence of these extrapolation constants depending on the admixture of the exact Fock exchange, so the Hartree-Fock exchange in hybrid functionals into the DFT recipe. So on the top, I have Hartree-Fock, which has no correlation. On the bottom, I have PBE, which is 100% PBE correlation and 100% PBE exchange. And in the middle, I slowly increase the percentage of Fock exchange while backing out the percentage of PBE exchange. And as you can see, again, the triangles are the means and the orange lines are the medians. It converges rather nicely towards the Hartree-Fock limit. However, I tried to look whether a recipe could be based on this relationship, and it doesn't seem to work that well. And I believe part of the answer is this huge variation among density functionals. So on the left-hand side, I'm showing some popular density functionals. And again, the positions of the means varies quite dramatically. There are our favorite outliers from Minnesota, which just require completely different approaches than anything else. But most of the functionals which I looked at actually fit into this sort of sweet spot around 1.3 to 1.4 with exponential extrapolation. So I thought there might be some benefit to this. And I'll just quickly show you one slide of the results from this paper, which on the x-axis, I'm showing you the weighted total mean absolute deviations from Lars Gurik's GMTKN55 dataset. Actually, it's a reduced version of that dataset. So this is performance for main group thermochemistry, for non-covalent interactions, for ionization potentials, for electron affinities, and so on. And as you can see, in the background, I'm showing the different values one can obtain with increasing the larger basis set. So from 2 zeta on the right-hand side to quintuple zeta on the left-hand side. And the dots, the orange dot and the white dot, are two chosen different extrapolation methods. And we can see that definitely there is a systematic improvement over the triple zeta calculation. This was done with correlation consistent basis sets. Actually, the method performs even better if one uses, for example, the Karlsruhe family, the DF2 with augmentation. So for the basis sets that we would like to use for example, non-covalent interactions, which are diffusely augmented, the extrapolation performs actually extremely well, and we can get results there of quadruple zeta quality at the cost of double and triple zeta. That is everything I wanted to talk to you about today. I feel like I've rushed through the slides. I would like to thank the Forest Research Foundation for funding, the people at Curtin for welcoming me into their group, so that's Julian Gale, Paolo Reiteri, and others, and obviously my colleagues at in Hanover who have been involved in the first part of this work. Thanks.
Thank you, Peter. This is wonderful. I mean, you have shown us what possibilities we can achieve using this new method, this new suite of this new approach, right? Okay, so we have several questions here. So we have the first one from Lars. So maybe I'll just unmute Lars. So Peter, can you see it from the chart, the chat function?
Yep.
Question, yeah, I'll unmute Lars so you can have a conversation. Lars, I hope you can.
Yeah.
Yep, there we go.
Hi, Mark. I do just
Hello.
want to read out the question. So that's about the Minnesota functions, what you said at the
Uh-huh.
end. Head Gordon once showed that even at the quintuple zeta level, some of them aren't converged. They actually diverge.
Yes.
So I assume that's probably why you see that weird behavior. Now, would you then say, and that's my question, that like a CBS double zeta, triple zeta extrapolation would actually not work for them? Or even if it did work technically, you can't really rely on those results and you would go to, I don't know, a quadruple, quintuple zeta extrapolation?
Right. So in my opinion, doing a quadruple, quintuple zeta extrapolation, or even triple and quadruple zeta extrapolation doesn't really make sense, because at that point, in my opinion, you might as well want to do a coupled cluster of triple zeta quality.
For normal functions, but not for those. So.
I was really surprised. So for these functionals, it doesn't actually show that well. So the Minnesota is the 6th on the list, and the M06L is the 3rd from the bottom. But even though I'm using an alpha that is not tailored specifically for the Minnesota functionals, there is still an improvement with regards to your data set, right? So what is really interesting, though, is that there is this DLDF, the dispersion less density functional, which was designed as a counterfoil to the Minnesota functional. So the Minnesota functionals were trained on a data set that had some compounds which had dispersion, which required dispersion to be described correctly. So the functional itself tries to mimic dispersion interactions, especially at a medium range. Then the guys, I can't remember who wrote this functional off the top of my head, the DLD functional was trained on the same basis set with the same functional form, but dispersion effects were removed. What I found really strange was that when you actually do, even when you go to triple to quadruple zeta with this functional, the performance for the GMTKN database, it goes down. Like the best basis set with that functional seems to be the double zeta. So this might actually be part of the reason, or it confirms the results you just mentioned, that it's oddly behaving functional. But I would not say that you shouldn't use extrapolation. So if you, I think actually they perform, they get you towards the peak of quadruple zeta using the double and triple zeta, and that seems to work reliably. I haven't tested it on much so far, so we'll see.
Yeah, thank you.
Thank you, Lars. Our next question comes from Laura.
Yes, I see the question. I did use the polarization consistent functionals family. It's included in the paper. They actually do not perform that well. So so the extrapolation doesn't perform that well. They perform well compared to coupled cluster, compared to a correlation consistent basis sets. So with the individual basis sets, you get better results than with the correlation consistent basis set. But the extrapolation methods don't seem to perform that well. And this is actually interesting because one of the only people who have tried or who have published something on DFT extrapolation was Jensen, and he used his own basis sets, and it doesn't work for them. So it might be just a case of, well, you know, it doesn't work with this stuff. It might not work with the other stuff.
Thank you for that. That makes sense. The other, that actually is really interesting, and I'll follow up later. The other question I had is do you know anything about the integral package in Psi4? Is the integral package pretty easy to modify?
It's being replaced out from Libent 1 to Libent 2 right now. So Ande Simonet is probably the person you want to talk to. I know that
name somewhere. Yep.
Yeah, I know that they go through, I'm not a C++ programmer, right? They go through a really painstaking process of making sure that I think there's Cmint and one other libERI, that the Psi4 interface is agnostic to the integral package you use. So if you have your own integral package, you can plug it in, and there might be interest in talking to these people so that the interface is designed properly. I don't know how you would go about modifying libint. I think that's something to speak with Ed Valer.
Knowing the people is perfect. Thank you.
Yeah.
I'll get the name off you later.
Yeah, sure.
Our next question comes from Andrea. I'll unmute you, Andrea. So, Peter, you can see the question, yeah?
Yes. Has the solvation package been updated in version 1.4 to support parallel processing? The answer is no. I have been working with Paolo on some stuff and have been trying to use PCM. And yes, every time you go through, so unfortunately the PCM solver that is used in Psi4 doesn't support gradient. So if you want to do geometry optimization or frequency calculation, you have to do it by finite differences, which is costly. And it's only, I think, single core. However, the cost is not really that much if you choose the cavity size appropriate to your molecule. So I had a huge number of points in the cavity, and then essentially my calculation, even on 4 cores, was maybe 30 or 40% utilization on average. If I went down with the number of points in the cavity, then it spends less time in the PCM. The quality of the results doesn't really change it much, and yeah, that's the way to get around it. But yes, it's a weakness.
Thank you. I guess I've got some benchmarking to do then.
Yeah.
Very well.
Just to mention that 1.4 is not released yet. We are in the process of merging some of these giant pull requests together. Hopefully, I don't want to give dates, that's not my job, but hopefully it will come out soon.
Very well. Our next question comes from Tim.
Yes, how do I define converge for those functionals? So I selected functionals which are not double hybrids. So to have a convergence, we need some sort of a complete basis set value, right? For Hartree-Fock, it's quite easy in quote because there are data sets. Yeah.
I meant that specifically for the Minnesota ones, which are, well,
right. Okay.
kind of answered already.
Yeah. One thing I wanted to mention that these reference data for all these functionals is actually calculated using HealthM, so the code by Sociolectula. He has enabled the use of libxc. So all the density functionals in libxc are in principle available in a finite element code, so you can calculate diatomics really easily. I spent maybe 20 minutes looking at the code, and it's really well done. So if you want to make reference results, then that code can be recommended.
Thank you.
Very well. Our next question comes from David. David, can you actually unmute yourself? Yeah, here we go.
I was just wondering how much do grid effects influence things? Because typically, if you're going to go to a bigger basis set, you probably want a tighter grid.
Yes. So I have used the standard grid that is used in Psi4, which is I think 302 radial points. I can't remember the number of the sorry, 302 angular points and 75 radial points, I think, which might not be great for a quintuple zeta basis set. I do not know whether the grid affects these results. The values which so these values on the screen, which I'm showing right now, they are actually done based on a really high grid. So the GMTKN stuff has been calculated using a standard grid because that's, in my opinion, the use case one would use generally without fiddling too much with the parameters. But the fitting of the alphas has been done using, I think on around about 1,000 points in the axial direction, and I think over 100 in the radial direction. So those, I think, are reasonably convert values with grid. Of course, scan, for example, requires a large grid. So it's a meta-GGA functional. it struggles when you don't give it about 100 radial points. So I just chose one which converged with scan, and then used everything, then used the same grid parameters with everything else for calculating these alphas that are in the middle of the screen. On the right-hand side, I have used a smaller grid.
So yeah, I'll post a comment there. I'll post in terms of those polarization consistent basis sets. You know, I discussed this with Frank years ago, but because they're all contracted using a particular functional, that can cause issues of convergence. So if you do uncontract it, and if you just uncontract the outermost function of each SPD, the orbital angular momentum, that makes a big difference to your convergence.
Good to know. I'll write it down and add it on the list of things to look at.
Peter, when are you going to put Gaussian out of business?
Well, I think they do a decent job of doing that themselves. It's crazy how much the licensing costs, but that's a different question. One thing which Psi4 needs and which I want to work on, if time permits, is anharmonic, second order anharmonic vibrational perturbation theory that is currently in Gaussian, and that's why I used Gaussian to get the equilibrium-like structures based on the experimental data. But adding it into Psi4 will be quite easy once I'll just show the slide over here. So I was talking about the distributed driver. Well, I can't find the slide, doesn't matter. And with the distributed driver, it essentially becomes the only problematic part is generating all those displaced, doubly displaced geometries, because you need to do a displacement along a displacement to get the second order vibrational perturbation theory. Once this is done, and I don't think it will take a long time, then we could push, at least from a rotational spectroscopy point of view, we could push Gaussian out of business.
Very good. We really look forward to that. I think Tim has a question, but I think we're sort of going way over time now. So you can see the question there. Probably I suggest that you maybe have a conversation with Tim about that now.
Yeah.
Okay, Laura. Now, Laura, are you available?
Oh, yes, I'm available.
Right.
So I think basically what we're going to do now is set everyone into breakout rooms. So thank you very much for coming along. If you don't want to join in the breakout room, thank you for coming along, and probably now's the time to leave so that we can set people up into breakout rooms. Is that correct?
Yes. Thank you very much, everyone.
Kicking people out.
And